Uh, Good morning, everyone. I want to welcome you to my lecture today. Before I get started today, I got some announcements. Number one, of course, your midterm one results will actually be upgraded latest on Thursday this week. And of course, the latest assignment will be uploaded today. I waited because I realized that you wrote midterm on Friday, and of course you need some relaxation. So when I post it today, Monday, of course it's going to be due for submission next Monday. So I decided to delay the posting of that assignment just because you wrote your exam just this Friday. So you've actually going through a lot. So I don't want to compound that. I also want to use this opportunity to tell everyone. I noticed the number of students that came for exam on Friday. If you compare that number with those in attendance now, of course, at any reasonable level of significance, there's a significant difference. So I think from Wednesday, from next lecture, I'm actually going to take attendance very, very seriously because, you know, um, those who stand a chance like of getting an excellent grade in a course, you know, those are the students who actually attend lectures and they ask questions and where they needed clarification. Of course, they basically gonna ask, and if they cannot ask during the lecture time, I know they basically are going to visit during the office hour. So I want to encourage everyone to be punctual, and then attendance of lecture, like I said, is very, very crucial. Okay, so I want to welcome you to this topic. We started before the midterm. Of course, I've been able to address type 1, but I'm bringing type 1 again, because I really want you to see the difference between type 1, type 2, and type 3 sum squared. So in today's topic, we're actually going to focus on this type of sum of square. Now, the question is, why do we find ourselves in a situation where we need type 1 or type 2 or type 3? Now, I want to tell you that when you want to compare, means in more than two groups, maybe you have one independent variable that is categorical, or you got two independent variable or more that are categorical. Of course, we're basically going to use analysis of variance technique. And of course, the analysis of variance technique enable us to be able to test, and the analysis of variance technique allow the total sources of variations to be splitted into various components. And the analysis of variance technique was able to do that using sum of square. I'm going to say that again. We were able to split the total sources of variation into various components using analysis of variance, and that become possible because of the sum of square. Without sum of square, there's no way we'll be able to do that. And of course, I want to tell you today, we got different sum of square, okay? And we got situation under which, any of these can actually be used. Okay, so if you look at the outline, you actually see that the type of the type 1, 2, 3, 3 sum of squared, we want to look at that in unbalanced data. Now, let me tell you this. When I'm working with a balanced data, what do I mean by balanced data? What I mean by balanced data is just like I have the same number of observation in each group that I actually want to compare. Of course, you can use any of these type of sum of square because they're basically going to give the same results. I'm going to say that again. Working weights, balanced data. Of course, you can use any of the type any of these type of sum of square, whether type 1 or type 2 or type 3. They're basically going to give you the same results. Then I'm also going to tell you this. When you're only focusing on one-way analysis of variance, whether balanced or unbalanced, I'm going to say this again. When you are working with one-way analysis of variance, when I say one-way analysis of variance, I mean I have just one independent factor, just one factor, but with levels. Whether balanced or unbalanced, all this type of sum of square will be the same. But when do we normally have issue? We normally have issue with the type 1, type 2, type 3 sum of squared when we are working with two-way analysis. Let me just say with two-way and beyond, where we have unbalanced data. Like for instance, whether you are working with one-way, two-way, three-way, and so on like that, if your data is balanced, there's no problem with type 1, type 2, type 3. But we normally have issue, okay? We normally get different results with type 1, type 2, type 3 in a situation where we are working with an unbalanced data, and that very unbalanced data have to start from two-way analysis of variance. Okay, so because of that, I'm actually going to walk you through what what is the difference, between the type 1, type 2, and type 3. In fact, we have more than that. We have type 4, except that I'm only going to be focusing on just type 1, type 2, type 3 in this, course. Now, let's start with the type 1. What do we mean by that? Let me tell you this. The type 1, when you are working, let's start with the two-way analysis of variance, where you got two independent variables. Of course, if you want to start, you're basically going to call one a factor A, you're going to call the other factor B, and you're going to call the another one factor AB, which is the interaction. Now, let me tell you this. If you call the one you call factor A will be the one that will receive the maximum variation when you are looking at type 1 sum of squared. I'm going to say that again. Type 1 sum of squared, we assign the largest variation. We assign the largest variation to factor A. The largest of the variation, largest of the variation to factor A. Okay. And in the remaining variation, we assign the largest to factor B in the remaining variation. And we assign the variation to the largest variation to factor B. After that is done, in the remaining variation, we assign the largest to interaction. And the remainder will go to the residual. Does that make sense? That is how type 1 work. So which means type 1 is another name for type 1. Another name for type 1 is sequential. Okay, it's also called sequential because order do matter. Order do matter. Okay, so when you name a factor A, okay, that will receive the largest variation. Okay, so order matters. So that's why it's actually called sequential. And of course, that is what you see on the board. Okay, you start with the SSA, right? Okay, it means it's basically going to assign the largest variation to factor A. Now, when you take a look at the second one, what do you see? SSB giving 1, A, which means the remaining variation will now be given to factor the largest of the remaining variation will be given to factor B. Don't forget, the largest variation has already been given to factor A. Now, when you take a look at the third one, SSAB giving 1 comma A and B, it means the remaining now, the largest of the remaining variation will now be assigned to AB. And the remainder will go to the error. So that is how, type 1 sum of square actually work. But let me tell you this. Like I said, the type 1 sum of squared is an appropriate sum of squared, when you are working with a balanced data. When you are working with balanced data and you start from two-way and over and above, type 1 sum of squared, okay, it's actually the best. And how do I know is the best? This is the way we're going to know. If I have two factors and I decide to make one a factor A in one module, and when I make factor A in one module, I make it factor B in another module. If I have the same result for them, then it means that type of sum of square can be trusted. I'm going to give you an example now. You're looking at the effect of education and gender on salary. It's a two-way ANOVA. As you can see, we got a balance data, and of course, this is the box plot for that. Now, let's take a look at this. In the first ANOVA, do you know what I did? We make gender to be factor A and education to be factor B. In the second ANOVA, you know what I did? I made education to be factor A and I make gender to be factor B. Now, you know what we need to do now? We now need to compare the sum of square for gender in the first ANOVA with the sum of square for gender in the second ANOVA. Oh my God, they gave the same result. Do you know the reason why the result is the same? Because we've used type 1 sum squared. Type 1 sum squared will give the same result, okay, for, whether you put one factor A or you put the other factor B, it doesn't really matter, provided you are working with a balanced data. Any question on this? Any question? The same thing also applicable to education, and the same thing applicable to interaction. I wanted to take note of that. Now, let's take a look at another data now. Oh my God, take a look at this data now. We've deleted some values. This, if you take a look at this layout now, this is no longer a balanced data, okay? And since we're now having balanced data, let us now try type 1 and see whether it's still going to be consistent. Take a look at what I have now. I want to try type 1 again. This time around, I'm trying type 1 on unbalanced data. Now I started with a gender. Okay, I make a gender as a factor A, education as a factor B in the first ANOVA. And of course, I switch that in the second ANOVA. Oh my God, the result is different. You see that? The result is different. So which means type 1 sum squared is not an appropriate sum squared for situation where you have unbalanced data. Type 1 sum squared is not appropriate for situation where we have unbalanced data. You can see that now. Okay, now what is now appropriate where we have a balanced data and we're working with it two-way ANOVA and beyond? We're actually going to consider either type 2 or type 3. Okay, now that's what we're going to consider now. Because of that, I want to walk you through into type 2 now. Is anyone who want to ask question about type 1? Okay, you are good, right? Now we want to go into type 2 now. And of course, let me tell you how type 2 work. In type 2, we don't consider interaction. We're going to focus on a factor after we've already adjusted for another factor. if you take a look at under the two-way analysis of variance now that you have SSA given 1 and comma B, it means I'm focusing on factor A, given that I've accounted, given that I've adjusted for factor B. And when you take a look at the second one, I'm actually the SXB giving 1 comma A means I'm actually considering factor B, given that I've already adjusted or I've accounted for factor B. Take a look at that. That's what we call sum type 2 or sum of squared. You know, type 2 sum of squared, it is actually called hierarchical. You know, type 1 is called sequential, right? But this guy here is called hierarchical because in type 2, order do not matter. The order of the factor do not matter. Okay, I'm actually going to walk you through an example of that now. Now, let me tell you this. When you take a look at statistical packages, we have a good number of them. We have R software, we have Python, we have SAS and so on like that. But let me tell you this, what is common to R software is type 1 sum of square. That is what is common. But you know what, we can also get type 2 and type 3. If we want to get type 2 and type 3, we need to specify that. I'm actually going to show you how to specify that. But if I want to get type 1, we don't need to specify type 1 because R is popular with type 1. Python is popular with type 2. SAS is popular with type 3. But let me tell you, in the framework of R, we can get all the type. In Python too, we can get all the type. In SAS too, we can get all the type, but except that I'm just trying to tell you the one that is popular. And you know what, if you want to have access to type 2 and type 3 in R, you need to load a package called CAR. Take a look at that. And if you take a look at this now, you know what I want to do? I want to work with unbalanced data where I'm looking at the effect of gender, education, and salary. And as you can see in my code, you can see type equal to 2, right? Can you see type equal to 2? So type equal to 2, it means I'm trying to tell R I need type 2. And don't forget, you need to load a package car to have access to that. Okay, now let's take a look at the result. Now, this is the result. Now, what happened here? When you use type 2 on this data, you know, whether you put gender as factor A or you put education as factor A, it doesn't matter because when you see the two ANOVA that I'm displaying now, they give the same results. But do you know they did not give the same result with type 1? But they now give the same results with type 2. I wanted to look at the gender in the first ANOVA. The sum of square was 30.462. In the second ANOVA, it was also 30.462. In the first ANOVA, here, gender was treated as a factor A. In the second ANOVA, gender was treated as a factor B. Even though you've altered the arrangement, the fact that you are using an appropriate, sum of squared, you are good, you are good. Any question on this? So which means we just justify using type 2 when you are working with your balancer design. Okay, now that's exactly what we've already done. But let me tell you, what is the difference between type 2 and type 3? You know, type 2 and type 3, I'm actually going to say the two of them work greatly when you are working with unbalanced data, but when the interaction is not expected to be significant, I'm going to say that again. When interaction is not expected to be significant, then type 2 is more powerful than type 3. I'm going to say that again. When interaction is not expected to be significant, type 2 will be more powerful than type 3. That is when interaction, because at times we know a lot of things ahead, of our research. You know why we know a lot ahead? Because we normally review literature. We read articles. Nobody goes into research with an empty mind. We always have something in mind. What if you have some, what you have in mind? You understand your research, like, use your feed. Okay, somebody working in sociology, somebody working in biology, you understand your feed. What happened in your feed better than any statistician. Now, you know what, before you apply statistical method, of course, you have certain thing in your mind. You are an expert in your field. And if what you have in mind is that the interaction, you don't expect interaction to be significant, and you are working with unbalanced data, and your design is from two-way ANOVA and beyond, then type 2 sum of square will be more powerful than type 3. Now, when do we need type 3? Now we want to talk about type 3 now. We need type 3 also for an unbalanced data, but when interaction is expected to be significant. I think you can see the difference, right? Between type 2 sum squared and type 3 sum squared. The type 2 sum squared is used for an unbalanced design for two-way ANOVA and beyond, okay, when we don't expect interaction to be significant. But for type 3 sum squared, we use type 3 sum squared for two-way ANOVA and beyond for unbalanced design when we expect the interaction to be significant. Okay, now how does type 3 sum squared work? Now I wanted to take a look at, I'm going to talk about looking at the two-way ANOVA, the type 3 sum squared. We actually consider factor A after every other factor in the model has been adjusted for. Oh my God, every other factors in the model have been adjusted for, including interaction. That is the difference between the type 3 sum square and the type 2 sum square. Because when I was dealing with the type 2 sum square, we did not consider interaction at all. I'm going to take you back so that you'll be able to see what I'm talking about. Look at type 2 sum square. You look at under two-way analysis of variance. What you can see is A, okay, given that we've adjusted for B, and B, given that A has been adjusted for. In a two-way analysis of variance, we did not consider interaction. Even when I say we did not consider interaction, we basically actually talking about the interaction A-B. Okay, so if I take you, yeah, go ahead. Exactly. Yeah, that's a very good question. Three-way has a lot of interaction. The one it has three first order and one second order. Now, when you take a look at the three-way, if I want to get SSABC, for instance, now the SSABC has to tell me that I'm only doing that after I've adjusted for every order. So the situation changes when the ANOVA now increases. You get what I mean? So you can see in the three-way now, what we observe in two-way is kind of different for type 2 sum square when we're talking about three-way. So which means if I actually want to get the SSABC, right? It means I've already adjusted for A, B, C, A, B, A, C, B, C. If I want to get the SSBC, okay, I've adjusted for all of that. If I want to get the SSC, I've adjusted for just A, B, A, B. So which means I'm only doing that for factor C. So the factor that you see that we're considering factor ABC, factor BC, and factor C. So I understand what you mean. The situation changes when the ANOVA now increases. But let me tell you this. This is the situation. This is the same argument that statisticians have about type 2 and type 3 up to today. But majority of the statisticians believe that, of course, you can use any of the type 2 and type 3 for unbalanced data, but the only difference is look at the error at the end of the day. You know the error? The residual sum of square. I'm going to say that again. Residual sum of square. That is the error. Every design has error. Does that make sense? So that is what we normally, because I just said something now. What I just explained the other time only apply to type 2. When I get to type 3 and beyond, situation changes. And that is the reason why there been kind of controversy. And that's why statisticians just believe that, okay, you know what, for unbalanced data, go for either type 2 or type 3. And at the end of the day, what you're basically going to use to decide is your residual sum of square. And but when you're focusing on type 2 only, I'm sorry, if you're focusing on two-way ANOVA only, then that's so glaring. Okay, for two-way ANOVA only, of course, when your interaction is not expected to be significant, go for type 2. When it's expected to be significant, go for type 3. But situation where you actually increase from type 2 and beyond, that will change. And what you're basically going to use as a yardstick is just going to be the residual sum of square. Have I answered your question, right? Okay, that's a very good question. Okay, now, like I said, for type 3, you will normally consider one factor after we've put into consideration all other factors in the model. If you look at two-way, and I want you to see, even in the three-way, the same thing applicable. If you take a look at the three-way, if I want to talk about ABC, interaction ABC, then I need to adjust for every other factor in the model. Do you see the first one in the three-way? When I'm considering SSABC, okay, I'm adjusting for other variables in the model. When I'm considering the SSBC, I'm adjusting for others, all of them in the model. When I'm considering the SSC, I'm adjusting for every other variable in the model, okay? But when I go back, and if you look at it two-way, okay, you're actually going to see that the same, right? When I'm considering factor A, I have to consider every other factor in the model, whether with interaction or not. But if I take you back to type 2, let me take you back to type 2. Now, in the type 2, where if you look at the three-way ANOVA, if I'm looking at factor A, B, C, you actually also going to see that every other members are also repeated. Can you see that? But when you go to the SSBC, you are not going to see interaction anymore, because the belief here is that the interaction of ABC will only be captured once. If you look at the first one, can you see ABC? Do you see any area where ABC is mentioned again in the model? No. Okay, now, so that is just the difference between type 2 and type 3. And if you want to run that in now, I'm going to show you, where you indicate type equal to 2, you're only going to type equal to 3. Okay, you're only going to put for type 3. Okay, so that is that. Now, the last form of ANOVA we basically going to have, even though I did not report that here, it's actually what we call type 4. We use type 4 ANOVA situation where we have a missing values. Okay, missing values, I think I treated that the other time. When you have a missing values, maybe some of the cells that you are comparing are missing, we use type 4. Okay, we call, and another name for type 4 is good night. That's a very good night. Good night. okay, or we call it balanced. That's another name for type 4. Okay. I think type 3, we call type 3 marginal. We call type 3 marginal or orthogonal. Orthogonal. Okay, type 3 is called orthogonal. Marginal or orthogonal. Type 4 is called good night or balance. Type 2 is called partial sum of square or hierarchical. Hierarchical. But type 1 is called sequential. Type 1 sum of square is called sequential. Sequential. Okay, I think I showed you that before. So type 4 is good night or balance. Type 3 is marginal or orthogonal. So that's a name. But if you don't want to go about this, you can just simply call them type 1, type 2, type 3, type 4. Okay, I think I just mentioned that. Oh, okay, I think I mentioned it here. Look at that. I said some software automatically generate type 4 sum of square for missing cells. And I told you, we use type 4 sum of squares. If you look at the last paragraph here, okay, type 4 sum of square for missing cell. Okay, so take a look at that. And type 4 sum of square use the principle of type 3, except that you are working with missing cells. I'm going to say that again. Type 4 sum of square uses the same principle as type 3 sum of square, except that you are using type 4 on missing cells. Okay, now the next thing I want to talk about, to pull or not to pull. You know, what are we talking about? What are we pulling? What are we not pulling? Okay, interaction. I think I walked you through this the other time when I had a lecture online, that when an interaction is insignificant, we can pull that interaction, right? Okay, and I gave a condition under which they can be pulled. Okay, so take a look at this. I said the decision about to pull or not to pull a non-statistically significant interaction depends on whether the data from a two-way ANOVA or higher is balanced or unbalanced. Okay, if the data are balanced, okay, then they follow the previous recommendation. That is, pull the interaction time into residual if we got two conditions. Number one, you have a 10 or fewer degree of freedom for residual. And two, the F statistic for the interaction, F is less than 2. Otherwise, do not pull. I think I explained this to you during my lecture on Zoom. Was it on Wednesday? Yeah, was it Wednesday? Yeah, Wednesday. Okay. And if the data are unbalanced, then test using the full module. Do not pull at this point. Refeed the module dropping non-statistically significant time to obtain estimate for the time you retain. And the reason is that the estimate of module coefficient depend on what other terms are in the module when the data are unbalanced. So this is a condition under which we should pull or not. Now, let's go to the summary. What is the takeaway from what we've done? Okay, for balance, I said for balanced data, effects are orthogonal. You know the meaning of orthogonal? Effects are independent. It doesn't matter whether you order them or not, whether you order factor A or B or not, it doesn't matter because they are independent. Okay, and I said type 1, type 2, type 3 will give you the same results. Okay, for balanced data. And the reason for that is because in balance data, effects are orthogonal. It means effects are independent. And that is the reason why they're basically going to give you the same result. Now I said non-statistically significant interaction may be pulled into the residual if certain conditions are met. I think I just told you that. Now for unbalanced data is not an issue for type 1 SSL for one-way ANOVA. I told you. We are working with, the only issue that we have is from two-way and above. Okay, from two-way and above, when you have unbalanced data, do not use type 1 sum of square. When you use type 1 sum of square, you're basically going to mislead. I told you the other time, our modules are not failing us. We are the one that we're not doing the right thing. So we need to do the right thing. We need to follow the rule. Okay. For unbalanced data from two-way ANOVA and higher, okay, treatment effects are no longer orthogonal. You know what I mean? They are no longer independent. That's what I mean. And why is it that they are no longer independent? Because you have unequal samples, within the group. So therefore, say type 2 sum of square do not change values depending on the order in which factors are entered. The model like type 1 SS do. So we use a type 2 sum of square is the most powerful test when there is no interaction, as given by Langstrom 2003. And that was what I told you the other time. When there's no interaction, okay, when you expect that you shouldn't have any interaction, of course, the type 2, and you're working with the unbalanced, model. Of course, you're going to go with the type 2 because it's more powerful, okay? And then we know for missing treatment combination, be careful about the automated output that claim to address missing cells. So know what you are testing, okay? And that, test using the full model, refit a reduced model to obtain the estimate of coefficient that you retain. Now this complete type 1, type 2, type 3. Now we quickly want to go into, and let me confirm to you today in the following assignment I'm actually going to release tonight. I'm going to test, I will ask you to test on the balanced data. I will ask you to compute type 1, type 2, type 3 ANOVA. And on the unbalanced data, I'm also going to ask you to compute type 1, type 2, type 3 ANOVA. Of course, by theory what you should get. So that's what I'm going to give you today in the assignment. I'm actually going to release tonight. That assignment will be due the following Monday. Of course, I delay the assignment because you need to rest. You wrote a test on Friday. You needed some rest. That was why I did not post that yesterday. Okay, now we want to talk about another interesting statistical topic that we call blocking in design of experiments. This is different from two-way ANOVA. Even though students may confuse this with two-way ANOVA, we use a blocking a situation where we realize that we are working with the heterogeneous. Okay, let's go into agriculture now. You will understand what I mean. I want to plant, right? I want to plant maize in my farm. If I can only use the idea that we've been using before. If I realize I can plant my maize anywhere in my farm, anywhere, before I can decide that I can plant that anywhere in my farm, it means every land portion is equally fertile. They are the same, homogeneous. But what if in a situation where in my land, in my, where I want to cultivate, maybe this area is more fertile than that area, and that area, they are different. That's heterogeneous. In that situation, I'm actually going to introduce a block. I will need to test a variation induced by block. So that's what we mean by introducing block. At times you may be working with the one-way analysis of variance, and you now want to bring in if you want to test blocking effect. Blocking effect in the sense that when you look at the experimental plot as a whole, it is heterogeneous. It is not homogeneous. Take a look at what I'm showing now. We have 4 varieties of beans: B1, B2, B3, and B4. That is one way, right? But you need to decide how to arrange the plant in a greenhouse, okay? And each bench can hold 4 large pots, and I have 16 pots. Now the bench 1, the bench 2, the bench 3, the bench 4, they are not the same. But within bench 1, this bench, this is the same here. They are all the same here. But when I go from one bench to the other, that is different. It's just like maybe the way you are sitting now, sitting in a group. Okay, maybe this group is different from that group, is different from that group, is different from that group. If I want to test the effect, if I want to test, if I'm still considering factor A, you know what I'm going to do? I will put all levels of factor A in this group. I will put all levels of factor A in that same group. In different group, I will test for all levels. of factor of that factor. And that's exactly what I'm going to take a look at this. What am I considering? I'm still talking about one way ANOVA, except I'm bringing in the effect of blocking. And in each block, you know what I've done? In each block, okay, I'm testing the effect of factor, of that particular factor. The B1, the B2, the B, consider the B1, the B3, the B2, the B4. You consider I test for that effect in each of the block. Okay. Now a block is a restriction. When blocking is significant, that will improve the quality of your ANOVA. I'm going to say that again. When blocking is significant, it will improve the quality of your ANOVA. Okay, now this is a bus plot for that. And of course, we're trying to introduce a block because we realize that the entire experimental plot is heterogeneous. Do you know the one-way ANOVA that we have used before? We are using the idea of complete randomized design. That is called CRD. Complete randomized design means my experimental plot is the same. I can plant anything anywhere, but in a situation where they are not the same, where one portion of my experimental plot is different from the other one, then I need to introduce a blocking factor. And we call, if you don't introduce that, you will not be able to control for nuisance factor. Block is a nuisance factor. And when you do that, the technique will actually increase the precision of your test. Okay, that's exactly what and let me tell you this. We can have a situation. When I introduce just one block, we're going to call it randomized complete block design. Randomized complete block design. Do you know at times we could have more than one block? If I have two blocks, that will be Latin square design. Latin square design. It means I'm actually introducing two restrictions. Okay. If I have more than two blocks, I'm going to have a Greco-Latin design. Let me show you the picture of let me start with the first one. The first one that you're seeing here is a completely randomized design. That is the one we've been using, one-way ANOVA, the first one. But when you look at the second one, it is what we call randomized complete block design. In one bench, you will repeat, you're going to test the effect of the B1, B2, B3, if you look at the second one. But if you look at the first one, you're going to see in bench 1, B4 is repeated. Can you see that? If you look at the first column, B4 is repeated. In bench 2, B1 is repeated. That is a situation where you are using complete randomized design. Situation where you believe the entire plot is is homogeneous, where you use a one-way analysis of variance. But the second one is trying to say the entire area is not homogeneous, it's heterogeneous. And what you need to do in one block, test for all levels of the factor. That's what you see now. But look at another, in the second one that you see, we are only introducing one blocking effect. The blocking effect has levels. How many levels of blocking? 4, which is bench 1, bench 2, bench 3, bench 4. But how many levels of factor do you have? B1, B2, B3, B4. That is your main factor of interest. But except that, you are introducing the effect of blocking. But take a look at another one now. This is when we're introducing 2 block effects. Now, in the 2 block effect, the meaning? On every row and every column, B1 should appear only once. B2 should appear only once. Look at that. If you look at the first row, let's take a look at the first row. B1, B2, B3, B4. If you look at the column, also going to see B1, B2, B3, B4. Take a look at that. This is an example of a Latin square design. Latin square, the meaning of square. 4 by 4, 5 by 5, 6 by 6, 7 by 7. Okay, that's what I mean. That's why it is square. Okay, Now, how do we test for the, so let's look at the model. Okay. Now, if you take a look at what I'm trying to show now, a blocking model look like a two-way ANOVA without interaction. If you take a look at the model that I'm showing you now, it's looking like a two-way, right? ANOVA without interaction. But let me tell you, in the case of two-way ANOVA without interaction, each of that alpha and beta will represent, alpha will represent factor A and beta J will represent factor B. But in the case of a blocking, I want you to take a look at the way I'm going to interpret it now. Alpha high will test effect of factor A, beta J will test the blocking effect. Look at the difference. I'm going to say that again. Randomized complete block design, the way it is specified, where you have one block, it look like a two-way ANOVA without interaction. The difference between this model and that of two-way ANOVA without interaction is like in two-way ANOVA, alpha I will test the effect of factor A. Beta J will test the effect of factor B. But right now, okay, this is different. Alpha I tests effect of factor A, beta J tests the blocking effects. This is the ANOVA table for block. Do you see the difference between the ANOVA table for block and the one-way? A is a factor, the main factor, the blocking, and you are also considering blocking effects. But the only way you can tolerate blocking effect in your model when it is when it is significant. When blocking is not significant, you know what that means? When blocking is not significant, it means use one-way ANOVA. When blocking is not significant, it means you are working with the homogeneous area. You don't need restriction. That is what it means. But when blocking is significant, this approach will improve on the quality of your one-way ANOVA model. Oh my God, let's look at an example now. We have an example now where you are looking at the effect of variety on the yield, right? Effect of variety. How many variety do you have? You got 8 variety, okay? 8 variety, but you realize that when you look at your experimental plots, they are not the same. They are, they are heterogeneous. And of course, you can count like 5 differences, which that's why you're actually going to introduce a block restriction, which is block 1, block 2, block 3, block 4, block 5. Take a look at that. The levels of block here is 5, but the level of your factor is 8. The level of factor A, the only factor you are considering is 8, but the levels of block is 5. I want you to look at each block. In each block, you tested for the levels of variety. Look at that. Now, this is a coding out, and I'm basically going to show you. Let's look at this ANOVA result. Oh my God, look at the model. Look at what I wrote. If you take a look at this, we're using type 1 sum of square here because we're working with the balance model. You can see we did not specify whether type 2, type 3, type 4. And what is a variety? Variety is significant, right? It means there's a significant difference between the 8 levels of the factor. Let's look at the blocking effect. Oh my God, the blocking effect is also significant, which means you have improved on the quality of the model. Instead of just to use one-way ANOVA here, using one-way ANOVA with a blocking effect is better. This is a one-way ANOVA with a blocking effect. Because of that, it looks like a two-way, right? The second factor is not that factor, but a blocking factor. Take a look at that. Okay, so get a bus plot. Then we can look at if you want to look at the efficiency. Oh my God. Lastly, look at it. When I did not consider any block, what was the residual? 70,829. When we consider block, what was the residual? Residual is 37,433. Do you know why? There's a drastic reduction in the sum of square because the blocking was significant. Any question? Did you see the difference? Just like the question you asked the other time. Can you hear me? The question you asked the other time, if you really want to know whether a model perform better than the other model, we compare the errors. Take a look at this one now, the residual sum of square. Very, very small for the one with block, larger for the one without block. But we can only record that situation where blocking effect is significant. That is going to be the end of my lecture today. I hope you guys enjoying the lecture. Statistics is like a story. We are starting an entirely new topic on Wednesday that I'm actually going to call random effect model. Any question? Expect your result to be uploaded latest Thursday, midterm one. But from what I've been grading, oh my God, you guys are performing excellently. I'm beginning to have a confidence in this class. Good job, guys. But you're going to see the final result on Thursday. Bye for now, everyone.